So question number 3, a course is the first calculator inactive free response question. And I can see I've got a lovely little slope field. Let's look at 3. The depth of seawater at a location can be modeled by the function h that satisfies the differential equation h of t is equal to a half h minus 1 cosine of t over 2, where h of t is measured in feet and t is measured in hours. Afternoon t equals 0. It is known that h of 0 is equal to 4. So here we have the initial condition. What is this? This is depth, right? Okay, so I guess the initial depth. On A portion of the slope field for the differential equation is provided. Sketch a solution curve y is equal to h of t through the point 0, 4. Look how nice they were. They actually put you a little dot here so you couldn't miss it. So this is a pretty much free question. You just have to make sure that whenever you draw in your solution curve, that you're using the whole entire graph grid. So I need to go from 0 over here to the 5, and then just follow the pattern of the little slope fields. Remember that if you zoom in on your graph, each one of these is basically showing what the tangent line is supposed to look like. So I can see starting here at 0, we're at 0, 4. This has got to be what our graph is supposed to look like. It's got to follow this trajectory here. And then I can see that as soon as I get beyond here, the slope seems to be going up a little bit. It's increasing. So I'm going to follow those slope lines. So I'm just going to follow the pattern of this one because that's its tangent line right there. And then just keep coming up, and it's increasing here. And then notice that now they're starting to taper off. And I can see that there's got to be a relative maximum right in here because I can see the shape coming on down here. Okay, so we must be hitting our maximum somewhere around there. Now keep going, come down, and then just follow these little slope lines. And I think that should do it. I'm pretty sure that that's worth a single point there, guys. So +1, and that's it. Now, sometimes they have you draw a slope field, and if they have you draw a slope field, it might be 1 point, it might be 2 points, depending on how many points they ask you to approximate the slope field at. But here, just drawing a graph, okay, that's a point, and it's done. On part B, I think I have this down here. Okay. Between 0 and 5, it can be shown that h of t is greater than 1. I think this is going to be important here. Find the value of t for 0 is less than t, which is less than 5, at which h has a critical point. Pause here for a second. What does that mean? Critical point, search it up on the Google, and that means that h prime of t is equal to 0. It's where our derivative is equal to 0 undefined. Determine whether the critical point corresponds to a relative min, relative max, or neither a relative minimum nor a relative maximum of the depth of seawater at that location, and justify your answer. If they're asking for justification and we're looking for relative min and max, we have 2 options. Our 2 options include the first derivative test, and it just checks the sign of your first derivative. See if you're changing from plus to minus or minus to plus. If you go from plus to minus, that means your graph was going up and then it came back down, and you have a relative max there, correct? Yes. If your derivative changes from negative to positive, you must have a minimum here. Okay, first derivative test, fairly straightforward. Okay, and then our second option is the second derivative test. And the second derivative test tests for the same exact thing that the first derivative test tests for, which is relative mins and maxes. It just uses the second derivative instead. It uses the concept of concavity. So if your graph is a concave up kind of shape and you have a critical point on that interval, then that critical point must be the location of a relative minimum, right? And this is going to give us to have concave up kind of shape, you have a positive second derivative. So put a little plus in there. And then if we have a concave down kind of shape and a critical point on that interval, then that's going to mark the location of a relative max. That's going to be a negative second derivative. So either one of those should work in this case, I think. Sometimes one might be easier than another. And you know what I'm going to do? I'm just going to do them both. Let's start with the probably the obvious one, first derivative test, since it's given to us here. I'm going to snatch our differential equation. Copy and paste. Okay, so we need to first find critical points. And as I said, this is what we're talking about, that h prime of t, which is the dh dt, is equal to 0. So if I try to set this thing equal to 0 and solve this thing, so 0 is equal to a half h minus 1 times the cosine of t over 2. First thing to notice is this, it's already factored, right? So zero product property implies that maybe this quantity is 0, or maybe it's the second one is 0. Guess what? We get to eliminate this h minus 1 because it told us that h is always greater than 1. I have something bigger than 1 minus 1. That means that this value is always going to be positive. So I'm going to say something like, since h of t is greater than 1, then that implies that h minus 1 must be greater than 0, right? You can pretty much get that from just subtracting that 1 over this to the other side. So a 0 from this is only going to come from the cosine part of it. So I'm going to take this cosine, t over 2. We do know that cosine is equal to 0 some places. So where is those places? Perfect English. Okay, cosine is equal to 0 here at pi over 2, and then also at 3 pi over 2. Well, which one is it? Or is it both of them? Here, let's solve. So this pi over 2 that we just found, that's equal to the input, which is the t over 2 as this composite function here. So t over 2 is equal to pi over 2, multiplying the 2 over that t is equal to pi. Pi is about 3 according to Archimedes, so like that's in between this interval, so that checks out. Check. And let's see, what else we got? It's possible that we have t over 2 is equal to 3 pi over 2. If I multiply the 2 over, they cancel out, gives me t is equal to 3 pi. Now that's 3 times 3-ish, which is 9-ish. 9-ish is outside of the interval, so garbage. Okay, so our only critical value is t is equal to pi. All right, let's make sure at which, find the value of t. And so it just says find it, and we just did. So it's like an identify kind of level question. And then we have to say, hey, do we have a relative min or maximum there? And we're using, at first here, the first derivative test. You don't have to do both of them, you just pick one. But for the sake of review, I'm going to review both of them. So here, let's talk about the first derivative test. And it'll go like this. We usually set up some intervals. And the intervals are essentially breaking up the domain that they gave us, which is from 0 to 5. And that's going to be broken up at our critical point, which is pi. And then we'll go from pi to 5. And now we just need to find some x values. And by x values, I mean t values in each one of these intervals. I might do something like pi over 2 here. And I need something bigger than pi on my unit circle. So, I don't know, maybe this is 1, 2, 3, 4, 5 pi over 4. It should work. Right, and then we want to know what is the sign of h prime of t, or dh dt if you prefer. Okay, so if we were to stick in, this is back into our derivative here, Remember, this is always positive. You can disregard it. We only really care about the cosine of pi over, or t over 2. So if I plug in a pi over 2 and divide it by 2, I'm really taking the cosine of pi over 4. Cosine of pi over 4 is firmly in the first quadrant, meaning that that derivative is going to be positive, and h is going to be increasing here. All right, and then the 5 pi over 4. 5 pi over 4 is really, divided by 2 is the cosine of 5 pi over 8. So counting by 8s, this is over a half, right? Because 4 pi over 8 would be a half. So it's just to the left of that, which is in quadrant 2. Cosine in quadrant 2 is negative, making the whole derivative negative. And our function is decreasing. So I'm going from increasing to decreasing. I found myself a minimum. That is not what that is. It's clearly a maximum. All right, so right up here, because it does look for what justifying your answer, and I will say at the critical point, t is equal to pi, h of t has a relative maximum since, got to give a because, the table is not enough. Got to interpret the table. Since h prime of t changes from positive to negative. To negative at t is equal to pi. And you know what? Do you know what? I'll tell you what after I box this. Let's take a look at that slope field, shall we? Slope field is supposed to be approximating the solution curve that we came up with. And here's 3 pi-ish kind of thing. And if I come back right up here, I can see, ooh, sort of looks like a relative maximum right here. So this slope field, or our solution curve within the slope field, could have pointed us in the right direction of what it was that we were looking for. And then also notice this, the shape of this graph is concave down. Since it's concave down, second derivative test have a relative maximum on here at that critical point, which is what we were talking about here. Now, I can't use the graph to justify it. I have to use the derivative, either the derivative that they gave me here, or in the case what I'm about to do is take the second derivative. Is this extra? Not necessarily. It's just that sometimes it's the best way to justify your relative min and max, because there isn't a way to use the first derivative test as easily. Let me dupe this thing. This one I think can go either way. However, notice this. H right here is the dependent variable. Dependent. And as the dependent variable, this means that it gets implicit differentiation, since it does appear in our derivative that we're going to take the next derivative of. The t that's on the bottom, that's your independent variable, which is over here, which means that you're just going to differentiate t normally. So our second derivative, d2h over dt2 is equal to, I'm going to consider our first, I'm going to use the product rule here. I'm going to consider 1/2 h minus 1, the first function. And so the derivative of this would be 1/2, and then this h here, ordinarily that would just be a 1. However, since h is a function of t, I have to use the chain rule on it, and it would be h prime, or dh dt. So it's 1/2 dh dt times the second function, cosine of t over 2, plus, and then I take my first function, which is 1/2 h minus 1, times the derivative of the second one. So taking the derivative of the second one, I'm going to have to use the chain rule on this one because you have a composite function. Derivative of cosine of something is negative sine of something, so that's going to change this sign, minus sine of t over 2 times the derivative of t over 2, which is an extra half. All right. So this is where this one could have gotten tricky for sure, especially if you try to do the second derivative test and you didn't do this part implicitly, and then also you forgot the 1/2 on this chain rule component for the composite function, right? Okay. Anyway, so let's see what would happen now. What you're supposed to do is this. You take the value, your critical value, and you plug it into your second derivative, and you're just checking to see, is it positive or is it negative there? So the second derivative evaluated at t is equal to 0, no, pi, what am I doing? I would have 1/2 dh dt, you know what that is? That is 0, so times 0. Why is that one 0? Because we're evaluating this at its critical point. Its critical point is when the derivative is equal to 0. Times the cosine, not that it matters, the cosine of pi over 2. Who cares? This part is gone. Boop. Minus 1/2 of, I don't know what h is, minus 1. Maybe that's a problem. I don't know. Actually, let me just go ahead and multiply this half times a half, make that a fourth. That's sensible. And then the sine of pi over 2. Let's see, sine of pi over 2. I think that's 1, right? Sine is 1 right there, so this is 1. And, oh, it's coming up again, isn't it? H minus 1. H minus 1, remember h is greater than 1, which means that that guy is positive. So I have a positive times this 1, which is also positive, times this negative 1/4, making the second derivative negative. I believe it's just equal to a, well, I don't know exactly what number it is because I don't have the h value there. So I'm just going to say that it's less than 0, and that should cover it. All right, that was in green, so I'll just draw over it with blue so it matches. Perfect. Okay, so this gives me enough to justify it, and I am going to say that basically the same kind of thing that I said right up there, which is at the critical point, t is equal to pi h of t possess. Oh, I'm going to use the word possesses. Possesses. It's demonic. It possesses a relative max. And like, as far as this goes, whenever you are thinking through this, if you have a negative second derivative, you got concave down, and you have a critical point on there, just drawing a little graph will point you in the right direction that, hey, this is relative max. Maximum. Since, got to give that because, basically h prime of pi is equal to 0, so I showed that that is a critical value, because this part is important because all of the points on an interval where the second derivative is negative, I don't want to be confuse it with, oh, I pick a point over here, and the second derivative is negative here, so that means this point over here has to be a relative max. No, it only happens when you have critical points, so the first derivative is 0, and h double prime of pi is less than 0. And as far as justifying with the second derivative test, that's all you would have to say. First derivative is 0 there, and the second derivative is negative, so you have a relative max. Okay, so point-wise, what do I think? I'm thinking here, it's possible, it is possible that what we have to do is set dh dt equal to 0, because it is asking for critical points, it doesn't define it, so looking for an interpretation there, I think that that's what this is. Finding your pi is equal to, or your t is equal to pi as a point, and then your justification with your answer is worth a point, so I think that one's 3. We'll look for sure at the end of this. Okay, and then the final part. Separation of variables to find y is equal to h of t, the particular solution to the differential equation, blah, blah, blah. with the initial condition h of 0 is equal to 4. So usually this is quite a few points, like 4, sometimes 5 points. Let's see how much we have to spend if we had all of this correct. That was 1, and I said that this one is probably 3. So maybe 5 points on this, unless I miscounted someplace. Wait. Did I say 3? I think I said 3, right? So 1, 2, 3. Yeah. Okay. So let's see. Let's start breaking this thing down. And the first thing that I'm going to break down is the fact that it says use separation of variables. I can almost guarantee if you do not separate your variables correctly, you get 0 points on this. The max that you can have is whatever you got before it. And then also the second part of this, where it says y is equal to h of t, this implies that you need to solve for h. In other words, you have to isolate it. A lot of times what happens is that we'll have something trapped in an absolute value. We might have a natural log or something like that. You have to resolve all of that because it says y is equal to h of t, implying that we have to isolate the h. And then we have to make sure that we use our initial value. In order to use this initial condition, that means we're solving for c, and we have to have like that constant of integration in there. And that constant integration is always something that they're looking for whenever you're solving a differential equation. Okay, so I'm going to kind of color code some of this. H stuff is going to be this, and then our T stuff is going to be this. And let's go ahead and do our separation. So dh, and I'll have to divide this over, so h minus 1. And it's possible you want this 2 over here, like as in multiply this 2 over. I don't know. We'll just see. Is equal to the cosine of t over 2. And then what we'll have, bring the dt over. Don't forget that guy. And then we're integrating on both sides of this. Okay, I think I just changed my mind here. This 2, I think I want to put it with the cosine because this is going to use a u substitution, which is going to have a half in it, which we need a half in our integral. And we won't have to fix anything if we already have the half over there. Brilliant. All right, so we'll leave that as a half. So speaking of u substitution, technically both of these sides are u substitution. Over here, you have a composite function where u is equal to h minus 1, but your du is equal to dh, so there's really nothing to fix. And on this side, that means that my antiderivative, that's the natural log, it's du over u kind of form, so it's the natural log of the absolute value of h minus 1. Equals, okay, and now we'll have to do another u substitution, different from the other u substitution, where our u should be the interior part here, so u is equal to t over 2, and du is equal to a half dt. And notice that we do have that already. So there's a half, there is our dt, that is our du. So essentially this just became the integral of cosine of u du. And the antiderivative of cosine is just straight up sine, no negative sign. So sine of t over 2. And here's where you want to put your plus c. Don't put it later, put it right there. Okay, and so remember what we said. We do have to isolate your h in order to get full credit. And then we have to also use this initial condition. At what point you use your initial condition is kind of optional. I tend to use it as soon as possible. After I've taken those antiderivatives and I've found what my c value is, this is in the least complicated form here, so just go ahead and plug in your 0 for your t, boop, and plug in your 4 for your h, and see what your c is. So I'm going to have the natural log, absolute value 4 minus 1. Remember, you don't get a calculator for this. Sine of 0 over 2, and then plus c. So sine of 0, that's over here, that's a 0. That's nice. So that's 0. That, of course, is 3. Absolute value of 3 is still 3, implying that the natural log of 3 is equal to c. And just leave it like that. And then rewrite with this constant of integration all up in there. natural log absolute value of h minus 1 is equal to the sine of t over 2 and then plus the natural log of 3. Very good. Now I can probably guarantee that you got most of the points already there, and then the final point is probably coming from actually isolating, getting the expression which isolates the h. So how do I get h out of the natural log? I have to exponentiate, of course. Exponentiate both sides. When I exponentiate the left-hand side as inverses, these cancel each other out, giving me absolute value of h minus 1 is equal to e to the sine of t over 2 and then plus the natural log of 3. But I'm going to use a property of logarithms to simplify this a little bit, as e to the sine of t over 2 times e to the natural log of 3. Because when I'm multiplying with like bases, I would add the exponents together. And then this piece over here, these are inverses, giving me a 3 for that portion, which I'll just bring out front because it looks a lot prettier. So I've got the absolute value of h minus 1 is equal to 3 times e to the sine of t over 2. And then, oh my gosh, I got to get rid of my absolute value. So usually what you got to do is get rid of these absolute value symbols and then go, oh, this is either a plus or a minus. But guess what? I don't have to do that in this case because, as we talked about in a couple other sections, at some point in this FRQ, they said that h is always greater than 1. And since h is greater than 1, that means that this is already positive and the absolute value does absolutely nothing. So I can rewrite it without it as h minus 1 is equal to 3e to the sine t over 2. Add the 1 over, so h of t is equal to, finally, 1 plus 3 e to the sine of t over 2. And there's our final solution. So point breakdown, I'm thinking that it was supposed to be 5. I'm going to say separation is a point, so there's 1. We had to find 2 antiderivatives, and maybe they're a point each, so point each. So that's 3. Fourth one is probably your constant integration. And when I say constant integration, that means that in order to find the constant integration, you had to have used the initial condition there. And then I would say your final point here is your solution. Did I count up 5? So 1, 2, 3, 4, 5. Let's see how we did. Where did I put the solution guide on this one? I didn't put this one side by side, so that's fantastic. All right, so here's our solution curve. This looks pretty similar to what's the one that I drew, and notice that it does start over here through that point and then follows our relative maximum somewhere around pi and then comes back down. Our scoring node solution curve must pass through the point 0, 4, extend to at least t equals 4.5. So if you start over there, they're like, nah, and have no obvious conflicts with the given slope lines. Only portions of the slope curve within the given slope field are considered. Okay, that's interesting. You can see it was just a single point. All right, on part B, let's see. It was 3 points, and it says the first point was considering the sine of dh dt. So I thought it was just, hey, setting dh dt equal to 0, but this is saying considering the sine of dh dt. And notice over here it says because h of t is greater than 1, then dh dt equals 0 implies that the cosine of t over 2 is equal to 0. And then it gave us our critical point, identifying that critical point is equal to 1 point. And then our answer with justification, and it says a relative maximum. And let's see what their actual justification was. It says the first derivative in between 0 and pi was positive, and between pi and 4, the first derivative is negative, going from positive to negative, increasing to decreasing. You have a relative maximum. So this is the first derivative test. Let's see what they said about it. First point is earned for considering, I was actually right. Considering that dH/dt is equal to 0, so they actually give you the point if that's what you did. when it said consider the sign of this. Or look at all these other ones that you could have considered, right, to get that first point. Second point is earned for identifying t is equal to pi with or without supporting work. And I would say that makes sense here because all it says was find the value, right? Let's see, a response may consider h equals 1 or t equals 1 as potential critical points without penalty. Extra information that may be wrong, and they still don't take off for it. Okay, that's fine. Third point cannot be earned without the first point. Third point, that's this answer with justification, cannot be earned without considering the sign of that or saying that the derivative is equal to 0, whatever. A justification, third point cannot be earned with, I already said that. Third point is earned only for correct justification or correct answer of relative max. The justification can be shown by determining the sign of dh dt as a single value in this interval and a single value in that interval. That's the first derivative test. It's not necessary to state that dh dt does not change signs on this intervals. Okay, but that's actually how we did it. And then the third point can also be earned using the second derivative test. Oh, so smart. Here, let's see. Did they do this exactly the way that I did it? They did do some implicit differentiation. Okay, they have theirs in switched order, but that's okay. Here's this negative half times this was that negative 1/4 that we had before, and the sign, and then yes, it does look good. And they evaluated that at pi and said it was negative, so therefore it's the relative, the location of the relative maximum. Okay, so then finally the last part. It was worth 1, 2, 3, 4, 5 points. As you can see, that is super common, 4 or 5 points for a separation of variables to solve a differential equation. So the first point was separating those variables, and they separated exactly like we did, keeping the 1/2 over there on the right-hand side. You could have left it over here, but that just means that you would have had to fix the 1/2 for the t over 2. And then the other 2 points were each of the antiderivatives. Sometimes, though, it's just a single point for both of them. Here they had enough points to spend, and so they gave you a point for each antiderivative, which is the same antiderivatives that we got. A point for the constant of integration and using the initial condition. And they also got the natural log of 3, just like we did. And, oh, notice that it said in the same kind of thing, you can lose your absolute value since h is greater than 1. So they lost the absolute value right there. And then look right there, very clearly, 1 point for solving for h. And this looks exactly like the equation that we just came up with. So scoring notes, let's see. The most important one here is this one. And that is you get no points if you do not separate your variables. Let's see, a response that presents this as the natural log without the absolute value earns that still earns the antiderivative point. Actually, it didn't ultimately matter because h minus 1 was positive. A response with no constant of integration, this is also important, can earn at most the first 3 points. So that is, you separated your variables, you had your antiderivatives, but since you didn't use your constant, you can't get the last 2 points. A response is eligible for the 4th point only if it has earned the first point and at least one of the 2 antiderivative points. In other words, you can only get this constant of integration if you've separated your variables and had at least one antiderivative correct. An eligible response earns the 4th point only by correctly including the constant of integration in an equation and substituting 0 for t and 4 for h. So you have to use your initial condition and have a c present. A response that earns the 5th point only for an answer th of t is equal to blah blah blah, or mathematically equivalent expression for h of t, such as this. So notice that they didn't bring that 3 down from that natural log. A response does not need to argue that the absolute value of h minus 1, the absolute value of that is equal to h minus 1 to earn that 5th point. And then what is this special case response? That presents an incorrect separation of variables like this. So, wait. Oh, I see what they did. The 1/2 was over here, so it should have been a 2 over here on the left-hand side. Does not earn the first point because they didn't separate correctly, or the 5th point because they don't have the correct, if they don't have the correct separation, they can't get the actual correct equation here. but they are eligible for the 2 antiderivative points. Okay, so if you mess up your separation of variables, but you still do the anti-differentiation correct, you can still get some points there. All right, so that should wrap up question number 3 on the 2024 free response question test.